All right, so we're going to start with 14.76, which is question number 7 about the organ pipe and open at both ends. And what are the first 3 harmonic frequencies of this pipe? Express your answers with commas. So grab that. All right. 14.76. All right. So probably I would say the best why for this one would be actually doing the diagrams of the standing wave for the first 3 harmonics, kind of like we did in that lab. So I'm going to draw my tube 3 times, and it's open at both ends. So I'm going to leave it open at both ends. And then, so I know that at each end that's open, I have to have a node or an antinode. An antinode. And so the fundamental, or the first harmonic, has to be the smallest portion of the wave that can go from antinode to antinode and be in there. And so that would be something that looked like this. And with the one, so you have antinode, node, and antinode. And then the next one would need to go from antinode to antinode again, but go up from this. And if you remember from that lab, what's the separation from one to the next? Half a wavelength, always. Half a wavelength. So what's going to happen is I'm going to get 2 more nodes in here. And so I'm going to get a shape that looks like that. And then the next time it'll be another half a wavelength. So I'll get this. I mean, we can express that in an equation also, but I think it's fundamental to have that understanding. And so, good. So for that first situation, how much of a wavelength is actually in the tube? Half. And how much is in at the second? Well, and what's at the third? 1.5, or I'm going to write that as 3 halves. So as I go up, my wavelength is getting shorter or longer? Shorter, because more of it's fitting in there. So if it's getting shorter, what must my frequency do? Get higher or more, yeah. Because what's the same between all 3 situations? The medium, so therefore the speed. See how this theme keeps coming back? That the speed of the wave is fixed by the medium? It's kind of a reoccurring thing. So our only equation we really need is V equals lambda F. Okay. We're going to use, let's see, did they tell us what speed they wanted us to use for? No. So if we look at actually our equation sheet, I don't know if I listed it on there. I usually don't. Let's see if it's under our general stuff. So let's use, for the speed of sound here, let's try, I'm going to try the first one at, I'm going to say that this is in normal air. So 345. Someone want to grab our one of our textbooks and see what they look in the reading that's done on sound. What they give as their base speed for sound, because it could be anywhere from 340 to 350 depending upon 300s, I think. Let's look here. G block 500s, low 500s. Yeah, well, the beat frequency was reading was 5. Let's pause. All right, so it looks like in our book, the author likes to use 343 as their base speed of sound. Now, how do I know to use that rather than trying to figure out what it is in air at this problem? What other information would I need to know? No. I need to know the temperature of the air. Good, excellent. If they said this takes place at 15 degrees, when the air is 15 degrees Celsius, that's their hint to me that, hey, use that equation to figure out the exact speed of the sound. Since they didn't, yeah, since they didn't, we used it yesterday. Since they didn't, then I'm going to assume that it's 343. So for the first one, I'm doing, let's see, I need my lambda, I said half of lambda, right? Half lambda for the first one equaled 1.6 meters. So lambda must equal 2 times that, right? Which is 3.2 meters. And then for my next one, I have lambda equals 1.6 meters. Oh, I'm all done with that one. And then for the third one, I'd have lambda, or 3/2 lambda equals 1.6 meters. So lambda equals 2 times 1.6 meters over 3, which is, let's see, 3.2 meters over 3. So that's like 1.667 meters, right? Oh, did I miss the O? Thanks. I'm going to write that. That's not compressed. Equals 1.0667 meters. So now using B equals lambda F and V being 343, for my first one, I'm going to go 343 meters per second equals lambda 3.2 meters. And find F. So 343 meters per second over 3.2 meters equals F. And I'm going to call that F1 just so that I can distinguish it. And so F1 is 12 or so, something? No, not 12. 10 point something? I got 107. Did you use mine? 107 hertz. You okay? Oh, yeah. It takes about 10 minutes. Looking at my next one, speed stays the same. Now my wavelength has been cut in half, and I get F2. My wavelength is cut in half. What's going to happen to my frequency? Twice as big. So I hope I get an answer of 214. Let me see if I do. 343 meters per second over 1.6 meters equals F2, which equals 214 hertz. Yay. And then let's do the last one. Hope all these are right. Meters per second equals, what was that? 3.1.0. 0667 meters F3. F3 equals, I hope it's 321. And it is. Because since my frequency, my wavelength, a half of a wavelength more is fitting in each time, my fundamental frequency, should move up by my fundamental amount each time. Where do you want me to scroll up to? All right, let's move on to 14.44. All right, here we go. They want to know how fast does the car move. All right, so pedestrians waiting for the light to change. In a second, here's the car approaching with its horn blaring. The car's horn produces sound with frequency this, but the pedestrian hears frequency this. So this is 14.44. So they hear a higher sound. So the car, if they're, even without knowing which direction the car was, whether the car was coming towards them or going away, even if they hadn't told us that, could we tell that from the fact that they hear a higher sound? Which would it have to be? They're coming towards you because the waves are hitting you quicker, faster. So I might even put in my water. Car is approach since higher frequency. And frequency changes since speed of wave is, what's true about the speed of the wave? Yeah, I'm going to say it fixed by the medium. Very important theme, if you guys haven't picked up on that, is the speed of the wave being fixed by the medium. So, I'm going to grab our Doppler equation here real quick. Grab the snip. Now, mathematically, the way I've included the Doppler equation, I find it a little. there's a reason why it's written like this, which is not always the way you're going to see it in the book, because in the book there's multiple forms of the equation, and instead I write it like this and use a little bit of logic to decide which of these symbols I should use, because this equation will apply for all Doppler shifting problems, no matter what is going on. You use this same equation. Jack, those are chronological, so you're looking like the beginning of third term right now. If you're looking for a recent file, it'd be in the... Oh, okay, then you're in the right section. No, and that's what we're going to point out. Okay, so through a couple of logical, or looking at it logically, you can eliminate some of this. Which is moving? The source of the sound or the observer of the sound? The source. So we can get rid of, see where it says the observer? That's gone. I'm just going to cross that right out because the observer isn't moving. Now, did my frequency go up or down? Up. So this is what you hear. This one is what's produced. So we're saying the one that the observer heard is higher than the one that was produced, which is completely true. How do I get a number to be larger when I multiply it? Say it again, I couldn't hear you. Bigger than what? Bigger than 1. So that means that this whole part in the bracket must be greater, in this case, than 1. So I want this fraction to be greater than 1. Does that mean the top is bigger than the bottom? Or does that mean the bottom is bigger than the top? Top has to be bigger than the bottom to have it be a number greater than 1. Yes? Okay. So the top is in this case is fixed at the speed of sound. So the bottom needs to be smaller. Am I going to take the speed of sound and add another number to it, or subtract a number from it? Subtract. So now I've got it. I crossed out observer because they're not moving, and I put a minus on the bottom to make that fraction greater than 1. And now I have the equation that I'm going to use. So now it's just grabbing my numbers. The frequency I end up at, for me, is 387. That's the F prime. Yep. That's the one they hear, 387 hertz. It was produced at, for me, 381 hertz. Yeah. We're going to use our 343 meters per second for the speed of sound. Yeah. Unless they tell me, like, hey, the sound is in concrete, then it's going to be a different, or, you know, they tell me it's 50 degrees Celsius out. Then they're telling you, hey, figure out what the speed of sound is from that temperature. All right, so now, it's all numbers except for one variable. So, you guys need me to do the algebra, or are you good with that? Okay, well, let's see. My variable's on the bottom. That's not nice to deal with, right? So I'm going to take that whole bottom, and I'm going to multiply it on top, both sides, so that it transfers over. So I'm going to say, over here I have 343 minus, you guys okay if I drop the subscript and just make it V? Okay, and then I have 387 equals, and I'm dropping my, just to fit in here easier. So all I did is I took that bottom and brought it up. And then I want to get 387 on the other side. It's multiplied, so I have to divide. So I can do that. 3 minus V equals 381 times 343. Being real bad with my units right now, but oh, then that's minus, so I could plus to get it over to the other side, right? How does that move that? Yeah, I could add it to both sides. Yeah. Because eventually I want to get the V by itself, right? Yeah, you can do it that way. Yeah, there's lots of ways to manipulate this math. You could have also, at the point when you had all your numbers, thrown it in one of our solvers. That would have worked too. I got 5.32 meters per second. That wouldn't be good. So good on that first part, and it's because the sound is going to take twice as long to get back up here, up to it. But that time of 1.5 seconds isn't just the amount of time it takes the sound to get back up. It's how long the rock took to fall down plus the time it took the sound to get back up. That's the difference between this one and 4.16. In 4.16, you only have the sound going out and coming back. So those of you that have struggled or asked for it, my guess is you just took the time for the sound to go there and forgot that an echo goes there and comes back. All right, so don't forget that. All right, so in my Y, I'm going to put things like it takes time for the rock to free fall to the bottom. And time for the sound to travel back up. So I might even draw a little picture. Got our well. The rock travels down and is accelerating down at little g. The sound comes back up at 343 meters per second. The rock starts from rest. And what do you want to call the from the top of the well to the bottom of the well? What variable do you want to call it? I don't like X because it's going this way. Huh? Okay, we can call it Y. I was thinking H or D. We could do Yeah, we can do any of it. So let's do y. All right. So why not? So we've got the rock. The rock starts from rest. It's in free fall, so it's accelerating down at little g, and it accelerates the whole time. So we're going to use our good old friend that says d equals d naught plus v initial t delta t plus 1/2 a delta t squared, back from like the way beginning. We'll call the top of the well 0. We'll say it's v initial because it was dropped with 0. So we're left with that y equals 1/2 little g delta t, I'm going to put for the rock, squared. All right, so that's what the rock's doing. For the sound, we're going to use d equals d naught plus v initial delta t plus 1/2 a delta t squared. What's the sound not doing though? Accelerate. So that whole part goes away. It's going to end up at 0. It's starting at y, at actually, y. Plus, we know it's moving at 343 meters per second. And it will move for some amount of time. We'll call it delta ts. ds stands for sound. So we've got the time for the rock and the time for the sound. Are those two related to each other at all? Yes, they add up to 1.5 seconds. Yeah. So the time, which for me is 1.5 seconds, is the time for the rock to fall plus the time for the sound to come back up. Oh, wait, we have a y in both of those, don't we? Oh. Maybe we can combine the blue and the green together. We can say 0 equals 1/2 g delta t r squared plus 343 meters per second delta t s. Holy moly. I think I'd rather get rid of TS out of that equation. So I can do that by looking up here and saying, well, okay, so 1.5 seconds minus delta TR equals delta TS, right? And then if I substitute that in, 1/2 g delta t r squared plus 343 times 1.5 seconds minus delta tr. Hey, one variable. Maybe I should maybe it looks like 2 because g's in there. Let's get rid of g. And what's our value for the acceleration of in free fall? 9.81 meters per second squared times 1/2 equals 0, right? Oh, that's like a quadratic and everything. Those are no fun to solve, right? But maybe I can use a resource instead of my math brain. the bottom of our page, remember there are solvers. I think you could use Wolfram Alpha. I think I'm going to go to quick math. And see if that one will do it for me. If it will open. So I need to put it in here. My variable is going to be t. So let's see. 1/2 0.5 times, times 9.81 times t squared, t caret 2, right, plus 343 times, I don't know why I put parentheses around that, but why not? 1.5 minus t. 1.5 minus t equals 0. And solve. Your expression is incomplete. That's straight. Lots of processing. Well, I forget. And you know what? When it's deciding to be slow, we just try a different solver. You know what? I didn't care what t was. Oh, time for the rock. Interesting. Wait a minute. Yeah, I got a weird answer. I didn't get an I in my answer, but I got 1.53, which is longer than is possible. So I made a mistake someplace because it's only 1.5 seconds. Okay? So the sound, let's see, starts at Y. Oh, you know what it is? If we took down as positive, we need up here to be negative. So I dropped the negative from here. Because we have, and that's why we're coming up with a weird answer, because we set about an impossible situation. So I'll just make that negative. And let's see what it comes up with. Negative 71. Ah, there it goes. So 1.46913. That's the time for the rock. So if that's the time for the rock, how long does the sound take? .5 minus the 1.46913 is the time for the sound, which is what? 0.03 0 seconds. And then I can use that to figure out how far the sound travels.